Hello gentlemen, welcome to our video on 19.4 called Entropy Changes in Chemical Reactions. Now this is our last section dealing with entropy in this chapter. So, quantitative entropy values can be calculated and are tabulated experimentally as molar quantities in units of joules per mole Kelvin. We've done this before with enthalpy, delta H's. So molar entropies are usually observed under standard states. In the past, we've used standard states with this symbol here, the little degree symbol. That means we're at standard states, which hopefully you remember means that we are at two particular pressures and temperatures, or a particular pressure and a particular temperature. So 1 atmosphere is your standard pressure, and we got 298 Kelvin as your standard temperature. And at these states, we can calculate or tabulate, if that's our job, delta S. Now we only care about delta S because it's a state function just like enthalpy, delta H. So we can find delta S here by using that old summation equation. So we have our sum, that means sum, that's all, just add up all your products, their enthalpy values, accounting for the coefficient in the balance equation, minus the sum, that's a bad sum sign, sorry, the enthalpy values of your reactants. And you may or may not encounter this delta here going forward, doesn't matter. But these are values you would look up in a chart or in a table in the back of your book as you're doing this. So these values will be given to you to plug into the equation. So now, below, standard molar enthalpies generally increase with increasing molar mass. So things become more disordered or more random the larger the molar mass is, which means the larger the substance. So for example, methane has that chemical structure. Clearly we can see what that looks like. Ethane, meth means 1 carbon, eth means 2 carbons in your carbon chain. The prefix is there. And then propane, prop means, prop, say it that way, means 3 carbons in your carbon chain. So as your molecules get larger, as you go this way, your enthalpy increases. Because enthalpy is about randomness. It's about freedom of motion. As you increase the freedom of motion, you are more entropic. So just having, the very nature of having more electrons in bigger molecules gives you more freedom of motion. Here you have more bonds. With more bonds, you can have more rotation around these bonds, more translational motion, more rotational motion, more vibrations. So the more motion you can have, the higher the entropy. Okay, so a new concept here. 19.5 looks at this concept called Gibbs free energy. Now this is our last major topic for this chapter. We have this section and then one more. So Gibbs free energy is a state function that we use the letter G for, and it uses enthalpy and entropy to predict whether a reaction occurring at constant temperature and pressure will be spontaneous. So Gibbs free energy ultimately is what we use to figure out if a reaction is spontaneous in one direction or another. So Gibbs free energy, we use it to figure out the spontaneity of a reaction. Now, in blue here, I've put two alternative definitions or supplemental definitions that I usually like to use to help clarify what's here in black. So the first one, Gibbs free energy is looking at the amount of available energy that is present before or after a reaction takes place. So the word available is where free comes in. So it's kind of weird. Gibbs free energy. You know, in life, nothing's free, and nothing in that same concept is true here in chemistry. So it's not really free energy. It really means like available energy. And to help clarify that, I have to ask myself this question down here. To what degree has energy been released? So looking at the enthalpy. And to what degree has there been a freedom of molecular motion? Looking at entropy. So in a reaction, you're looking at, has energy been released? So you're looking at the enthalpy, and you're looking at the freedom of motion. Has that reaction become more entropic? If both of these things happen, then your reaction will happen spontaneously, or it did happen spontaneously. Now, spontaneity depends on a few things. So as a state function, it's going to depend on other state functions. In fact, the spontaneity depends on delta S, which is entropy. It depends on delta H. And it depends on your temperature. We're going to assume pressure is constant through this process. And even for right now, we're going to assume even temperature is constant in this process. But it does depend on these three things. So if we put that in equation form, delta G is a state function, so we really only care about the delta portion here. So delta G equals delta H minus T times delta S. Now, as you look at the spontaneity of a reaction, obviously you're looking at a specific temperature, meaning the room is a certain temperature, the vessel is a certain temperature. You're not going to have changing temperatures in here, so it's not a delta T here. It's just T. Now, a few things to look at. Let's say we look at how delta H and delta S change, or even temperature changes if you were to change the temperature, how that affects G. This is really mathematical, but it's still good to see. So as delta H decreases, that should be decreases like that, then delta G will decrease. As my entropy increases, delta G will decrease. And as, not what I want, as my temperature were to increase, delta G will go down. So now I'm looking at delta G decreasing in all these cases. And that's because one major highlight of looking at delta G is looking at the numerical value, because this is an equation. We're going to be calculating some things, and the numerical answer is really important. So if delta G is less than 0, meaning if it's a negative number, the forward reaction is spontaneous. So looking at delta G, we can figure out the spontaneity of the reaction by looking at the overall answer. Some more to go along with that. So if delta G is negative, they just said forward reaction is spontaneous. If delta G is 0, the system is at equilibrium. If delta G is positive, you guessed it, the reverse reaction is spontaneous. Okay, so we got a few things that we can now look at to understand better what delta G is and what it's saying about the spontaneity of the reaction. Now we can also calculate delta G beyond this equation here using standard states. Because it is a state function, all we care about is delta G here. So we can use it at standard states in the same way that we did with the enthalpy and entropy at this point, looking at our summation equation. Okay, we've used this before, so I won't go through any major examples now. I'll wait until we look at your problem set to do that. So gentlemen, please take notes and work on your problem set. Adios.